Yeah, there's a lot of background. Okay. Okay. Good evening, everyone. Okay, so please go ahead with your questions. Mahesh, my screen is not visible here. Whatever I'm writing, that's not visible in the YouTube. Whereas in the Google Meet, I can see. Yeah. Yes, thank you. Thank you. Yes, no problem with the out of week question. So long as it makes sense as far as the course is concerned, this is fine. So the LED modulation bandwidth depends on the radiative lifetime, whereas the laser diodes, it's not phonon lifetime, it is actually photon lifetime and the relaxation oscillation. Does radiative lifetime in laser, it doesn't have any role to play. So the answer to that is actually very simple. In case of laser diodes, actually the radiative lifetime will play a role through the photon lifetime also and through the relaxation oscillation. So what happens in an LED? You have the lower state, you have the upper state, and you have transitions happening from the upper state to the lower state, your conduction band to the valence band in a spontaneous manner. That's what happens in an LED, right? And so the lifetime of this state matters. Whereas in a laser diode, the process that drives emission is stimulated emission, right? Now, what happens in a stimulated emission? A random photon that got generated here gets actually reflected by the mirror, and then it comes back and it creates stimulated emission. That's how you can imagine how the stimulated emission process starts. So then, so what decides the rate of stimulated emission? The rate of stimulated emission is decided by the number of photons that is incident in the laser material. And of course, it is also dependent on the population inversion. How much inverted is your population? So which is why the radiative lifetime completely goes out of the picture, right? And the number of photons that are initially present is decided by, how reflecting these mirrors are, because it depends on how long the photons can survive in this cavity. And that's decided by the quality factor of the cavity, right? The larger is the reflectivity of the mirror in the cavity, the photons get trapped, or lower is the loss in the cavity, Larger is the reflectivity, which means that more energy is getting reflected, less energy is getting the photons are coming out of the system. A fewer number of photons are coming out of the system, in which case the amount of the number of photons that are available for stimulated emission becomes more, and hence the rate becomes faster, right? So that is why in a laser diode you do not really have much of an influence of the non-radiate, or rather the spontaneous lifetime. It depends on the stimulated lifetime, which in turn depends on the photon lifetime, and it also similarly the stimulated lifetime also when you're trying to create a stimulation close to the resonant frequency of the system, that is again the internal dynamics of the system, again that also is not we have learned that's not advisable, because that will create nonlinear effects. I hope that answers your question. Any other question for this week, or from any of the earlier weeks? So, Michael Jordan, you've been asking questions almost every week. So, I would like to know, where are you from? And in which college do you study? Which college, university do you go to? While I wait for him to answer, let's just quickly revise what we did this week, and then we can go through the assignment solutions for this week. I mean, not really against the solution, a method to solve. So what we saw this week was some key performance metrics and the erbium dope fiber amplifiers, right? Now, the key performance metric that we define are what I've written here. It's Q factor, and Q factor is defined as I1 minus I0 by sigma 1 plus sigma naught. Now, if you remember, how did we define the I1 and I0? And what we are doing this week is for on-off key system. So you said you had a high and a low, and I have drawing this high and a low with wiggles because that will have noise. So you have I1 as the current corresponding to one state, I0 as the current corresponding to the zero state, and you want to make a decision. So you want to find out where should I make my decision. Right? You're trying to find out what is the decision threshold. So the way to do that systematically is to work out the distribution in the one state and the distribution in the zero state. And if you have a distribution like this, there is a small section where the distribution belongs to zero, but then you could confuse it as a 1. Or there is also a small section where the distribution belongs to 1, but you could confuse it as a 0, and that's where you want to basically keep your decision threshold. And you derived in class as to how to find the probability. I'm not repeating all that. I'm just capturing the key results. So this I1 is a current corresponding to 1 state. I0 is a current corresponding to the 0 state. Sigma 1 is the standard deviation corresponding to 1 state. Sigma naught is the standard deviation of noise corresponding to the 0 state. The sigma 1 need not be necessarily the same as sigma naught if you have to consider both short noise and thermal noise. And we derived that this number that defines the data quality is I1 minus I0 by sigma 1 plus sigma naught. And this ID, which is basically your decision threshold current, is actually defined through this noise in the 1 state and the 0 state. So in principle, the sigma 1 square is short noise square plus thermal noise square. We defined short noise thermal noise last time. And sigma naught square is equal to thermal noise square because there is no short noise in the 0 state. The next quantity we defined to quantify the signal performance was bit error rate. And at optimized value of ID, when your sigma 1 and sigma naught are equal, I mean, you could actually calculate Q in terms of your ID, and you get that relation out there. And for that Q, your BER is related to Q through this simple function. This is complementary error function, and that gave rise to bit error rate versus Q. And that is a universal curve, and that doesn't depend on the data rate. This bit error rate versus Q does not depend on the data rate. So for Q is equal to 6, the BER is 10 power minus 9. Q is equal to 7, the bit error rate is equal to 10 power minus 12. So this is something that's important to know. So as far as a communication design engineer, you have to ask yourself the question, what is the error rate that I'm expecting? And typically, the standards would say that the bit error rate should be anywhere less than 10 power minus 12, or some of them would specify as 10 power minus 9, which means that statistically, you should not have more errors than one error when you are considering 10 power 12 bits. Again, it's a statistical quantity, so you have to really run the experiment multiple times, count the error in a really huge number of bits, and then find out the number of error bits and calculate bit error rate accordingly. But the good thing is that now we can define the bit error rate in terms of quantity Q, which is now defined in terms of the noise of the system, the signal current and the noise current of the system. Another quantity that is of use in a link design is the receiver sensitivity, and that you defined in class. It is related to the Q through this relation. And we also calculated in thermal noise limited regime, we found that the signal to noise ratio. So whenever we talk about signal to noise ratio in this section, we are talking about electrical signal to noise ratio. So we take the electrical power at the output of the receiver. The noise is always added in the receiver. So whenever we talk about receiver, we always talk about electrical signal to noise ratio. And if it is dominated by thermal noise, which is the case in most of the receivers, because the power levels are quite low in most of the receivers. So it is dominated by thermal noise, in which case the SNR is related to Q. We derived again, it's through a very simple relation like this. But when you have a short noise limited regime, we also said that now you can look at the quantum limited noise performance, and you can find out the BER there, because we can find out the BER through the number of photons. We moved on to erbium doped fiber amplifiers, and we said the output. So the output of the erbium doped fiber amplifier is square root G, where what does G represent? G represents the power output divided by power input. so that when you're writing in terms of field, it becomes square root G. And why am I writing in terms of field? Because I would like to add noise n of t as a complex number. That is why it is written in terms of field. But you can always find out what is the effect of this noise, and the noise always manifests itself after the receiver, right? So after the receiver, it manifests itself as a signal to noise ratio. So after the receiver, what you will have is the current, which is RD times Pin. Now this input, let's say for example, this is the erbium doped fiber amplifier. You had a certain Pin corresponding to an E in, and what it gives out is E signal plus E noise at the output, and E signal plus E noise is nothing but this E out, right? Which is square root G times E in plus noise of n of t. And if you expand this, we did this calculation in class. It turns out that along with the signal, there is always a band of noise that the erbium doped fiber amplifier adds, and that comes from the fact that there could be spontaneous emission in addition to stimulated emission. So typically at the output of the EDFA, you will always have an optical, so this is an optical filter, and this optical filter will have a certain bandwidth B0, and this basically cuts off the noise in the outside the signal band. So for example, I've shown a signal that's coming out of the EDFA with a bandwidth B0. Let's say the signal is at a center frequency F, and on either side of the signal, you're allowing a certain ASE band to propagate after the output of the EDFA. So in terms of, so this is the frequency axis and this is the optical power axis. If you look at the output of an erbium doped fiber amplifier, you will see the signal and you will see a noise, the blue band that you're seeing here, that is the noise band. Now, what is the consequence of having this noise band? The consequence is that when it falls on the receiver, so again, so you define what happens to the noise at the output of EDFA through a term called noise figure, which is simply the ratio of the output signal to noise ratio to the input signal to noise ratio. But again, the consequence of EDFA noise is at the receiver, and we derived what is the signal to noise ratio and what is the noise figure for the EDFA noise in terms of power spectral density of the ASE noise. So this noise that is added at the output of EDFA, you can exactly find out what does power spectral density mean? Power per unit bandwidth. Power spectral density would mean power per noise power, in this case, per unit bandwidth. So if you take a unit bandwidth, the power in that unit bandwidth, so if you take a bandwidth of 1 Hertz, the power in that, the noise power in that bandwidth is simply twice NSP. NSP is related to the inversion in the EDFA times H nu times the gain, right? So this is how you define the this is how you find out what is the power spectral density of noise. But look, you don't have 1 Hertz as the bandwidth. Your bandwidth is actually B0. So the total noise power would be this power spectral density. So this quantity that you see here is nothing but the power spectral density multiplied by the BO, which is B optical bandwidth, will give you the total ASE power in the optical domain. Now in the electrical domain, you can calculate what is the consequence of this, and that's what we derived later in the EDFA related lecture. So what we derived was we could derive this noise figure of the EDFA as 2 NSP G minus 1 divided by G plus 1 by G. And when G is very large, for large G, this is what you get, right? Now, if your G is extremely large, what happens is 1 by G is very small, G minus 1 by G is very small. So noise figure simply means is approximated to 2 NSP. NSP is the inversion. So if you have everything inverted, this is also approximately equal to 2, and that's the minimum value of noise figure that you can get from the EDFA. So the minimum noise figure from the EDFA is simply 3 dB. If I convert this factor of 2 into decibel, which means that what does it mean? If I go into the amplifier with a certain SNR, let's say this is my signal to noise ratio of let's say let's take an example. If I go into the EDFA with 15 dB signal to noise ratio, and let's say the signal power is minus 30 dBm and the noise power is minus 45 dBm, so that the signal to noise ratio is 15 dB, signal power to noise power. After it goes through the EDFA, the minimum noise figure is 3 dB, which means the SNR degrades. Let's say the gain is 20 dB, that is given by the EDFA. The output of the EDFA is going to look like this. The signal power gets amplified by minus 30. It gets amplified by 20 dB. Let's put a gain of 30 dB here, so that the signal power amplifies and becomes 0 dBm. Noise power should amplify from minus 45 to minus 15, but there is a degradation. So instead of minus 15, you will get minus 18 dBm, so that the signal to noise ratio at the output is, you will get something like, the signal to noise ratio has to be degraded. So 15 dB should become 12 dB with a noise figure of 3 dB. So the output noise power would be simply minus 12 dBm, so that the SNR is only 12 dB. That SNR of 15 dB cannot be maintained. And this is the reason why you cannot keep cascading an EDFA and keep propagating through infinite distance, because after every EDFA is a cascaded noise figure, and that results in the degradation of data quality. Okay, so these were the concepts that you learned. I would now go on to the assignments, but before that, if you have any questions, please type in. Does metastable lifetime has any effect over the modulated light? That is, if my modulated data pulse width is greater than or less than the metastable lifetime. It does. So that's again an interesting question. The question is, if the lifetime, the metastable lifetime in EDFA is 10 milliseconds roughly. So if you were to send a pulse through this EDFA, what you want, so this is the input pulse to the EDFA. You have a certain width, and what you want from the output of the EDFA is something like an amplified version of this. You don't want any kind of let me just draw this once again. You don't want any kind of distortion after this EDFA. So you want instantaneous response. You want the and what does it mean to have instantaneous response? It simply means that whenever you have input photons coming in, there should be photons available in the metastable state, which responds, which means which undergoes a transition to the lower state in accordance to or as fast as my input pulse. So in case of EDFA, the metastable lifetime is long, which means that you do have, because EDFA is an amplifier, it is a laser without the feedback, right? So it's going to, if you do not send a signal, what happens in an EDFA is only spontaneous emission. So you can assume that the upper stage of the EDFA is like a reservoir of inverted ions, right, which are ready to undergo de-excitation. So you will, and they are there for a long time, so the population is available for a long time. And if I draw the decay of the metastable state, so if it is N2 decays only with a time constant which corresponds to, as a function of time, which corresponds to 10 milliseconds. But now the data rates we are talking about is 10 Gbps and so on, which means 1 by 10 is 0.1 nanoseconds, which is 100 picoseconds. Now, within picosecond time scales, so picosecond I cannot draw in this set of axes. We are already at 10 millisecond. Now 10 picosecond is like 9 orders of magnitude smaller than this. So what it simply means is that when your input is coming at a very fast picosecond kind of time scales, you do have a population that is inverted, available for de-excitation, and so there is no shape distortion. Okay, but suppose you're trying to amplify something which is at very low rate. You're trying to amplify, let us say, 1 hertz. Of course, you're not going to send a optical communication. You're not going to operate at 1 hertz or 1 bits per second, right? 1 bit per second, which means that your on state is, let's say, 1 second long. And imagine a situation like that. The on state is 1 second long and the off state is like also 1 second long. Then what happens, right? So what really happens is after 10 milliseconds, which is 1 by 1000th of this, the EDFA has, let's take for ease of calculation, this is not 1 second, but let's say 20 milliseconds now. Okay, so I am looking at data rate, 20 millisecond on time, 20 millisecond off time. Let's make it 25 milliseconds so that it's easier to calculate off time. So my bit rate, bit duration is 25 millisecond. So your data rate is 1 divided by 50 milliseconds. Well, it's a non-return to 0. So the data rate is 1 by 25 millisecond, which is 0.04 kilohertz, right? Which is 40 hertz, right? Let's imagine, it's not practical at all, but since you asked this question, I'm saying, let's imagine you have a 40 hertz repetition rate. What happens is after 10 milliseconds, right? So this part of the pulse will start taking up all the population and the population decays at a rate of 10 milliseconds. But it does not really decay completely after 10 milliseconds because there is a pumping mechanism also working which is repopulating this upper state. So depending on the pump level, what you will have is that this you will start seeing something like this, right? And then it's continuously decaying, and when the pulse becomes 0, of course there is no response. So what you will start seeing is, instead of getting this as nice 40 hertz pulses, you will start getting something like distorted pulses. But for that, you should be working closer towards the metastable lifetime, and that metastable lifetime in EDFA is around 10 milliseconds, and that saves the day for us. So when you have faster data rates, your pulse is not distorted because of the EDFA. Okay, so I hope that answers your question. I also said that there are some things called as SOA amplifiers, semiconductor optical amplifiers. You can use them for amplification, but there the lifetime is faster. So the speed of response of SOA is something like of the order of hundreds of picoseconds, in which case you will start having these kind of distortion. These are called as bit pattern effects. These kind of distortions will be present if I'm using a semiconductor optical amplifiers. Okay. What else is the question? If there are, please keep typing your questions as and when you have it. In the meantime, what I would do is to go to the assignment section, and I'll keep discussing how to solve each of those questions. I will not give the answer as usual. So the first question is about binary modulated system without any waveform distortion. Normalized standard deviations and means are given. Normalized noise standard deviation. So sigma 1 is given. You have sigma naught. You have I naught. And you have I1, which are the average currents. What is the optimum decision threshold? Most of these questions in this assignment are simply formula substitution questions. So the optimum decision threshold, we saw you can calculate using this relation. So you have all the information to calculate that. Second part is how to calculate the Q and the BER. So again, once you calculate the optimum decision threshold, ID, you can calculate Q, and once you have Q, you can find out BER. If the normalized decision threshold is chosen to be 0.5 milliamps, which means that you are not really using the one which is chosen here, you are deciding to choose a normalized decision threshold which is not corresponding to that formula. The question is, how would the BER change? So the answer to that is you have to go back to that complicated BER expression. So you did derive in class that the BER expression is actually coming through the probability, right? And we derived in class that BER is equal to 1/4 complementary error function of I1 minus ID divided by sigma 1 root 2 plus complementary error function of ID minus I naught divided by sigma naught root 2, right? So now you know the value of I1 and I naught, you know the value of sigma 1 and sigma naught. What you're saying is that if your ID is not the optimal value and it is a value given by 0.5 milliamperes, what would be the BER? So you have to actually substitute in the complementary error function. You can calculate using a MATLAB or any other small code. You can write down to find out what is complementary error function. You can do it with a calculator also. I have given you the expansion of complementary error function. So from that, you can substitute and find out the BER. It will be surprising to see that you will get a very different answer in between the questions in 3 and 4. Even in the choice, if you see, in question 3, I got a choice of much smaller BER, whereas in question 4, if I did not use the optimal decision threshold, my BERs became higher, so I will get a larger error. So the idea of the question is to drive home the point that you better use the optimal decision threshold to get the best bit error rate. Okay, so any questions from that? It's nothing. So this we'll move on to the second set of questions. So for questions 4 and 6, some data is given. So direct detection receiver using pin diode. The responsivity is so this is question 4. Q is 6. Sorry. So responsivity is given. Responsivity is easy, 1 ampere per watt. Load resistance is 50 ohm. The bandwidth, I'm using B or delta F for bandwidth. Both remains the same, 10 gigahertz. It is NRZ modulated. We can neglect dark current noise, and the operating temperature is given to be 300 Kelvin. Now, use Q is equal to 6 and Q is equal to 7 for BERs of 1E minus 9 and 1E minus 12. Find the receiver sensitivity for these two limited by short noise. Now, how do you define receiver sensitivity? Receiver sensitivity, as we said, is the minimum power that is required to get a specific Q or a specific BER. Now, you know what is a specific Q that you need, and I have written this in the formula sheet here in terms of the for the thermal noise limited case, but you can do it for short noise limited case. And how do you do this for short noise limited case? So you start from the point where you have Q is equal to I1 minus I0 divided by sigma 1 plus sigma naught. Now, in the short noise limited case, what is it that you can use? Both sigma naught and sigma 1 you can take as the short noise. You're ignoring the, sigma 1 is short noise. Sigma naught is equal to 0 because there is simply no short noise in the 0 region. Short noise will be present only if there is a power present, right? So in which case your Q is, and dark current is 0. If the dark current is 0, it means I0 is equal to 0, which means your Q is I1 divided by sigma 1, which is I1 divided by short noise. Now you know how to calculate I1. I1 is nothing but RD times P peak power divided by, because I1 is the power corresponding to the one state. And short noise, we know what is the, how to calculate short noise. So you can, RD is given to you. You can, receiver sensitivity is always written in terms of average power. So you have to convert this into twice the average power because you are operating with non-return to 0. So the peak is twice the average, and you know what is the required Q. You know what is the responsivity. You have to calculate the value of average power, and this is what you are calling as sensitivity. And you do have information to calculate your sigma s. Okay, so that's very straightforward. Then you can calculate the receiver sensitivity for thermal noise limited condition. Now, thermal noise limited condition, I already gave you the relation. All what you need to do in thermal noise limited condition is you need to make sure that there is no short noise. In the thermal noise limited case, you should say sigma 1 is sigma naught, which is sigma t. And you have all the information for calculating the thermal noise. Then you have to calculate what is the receiver sensitivity considering both short noise and thermal noise, which means you are now recalculating the whole thing considering both thermal noise and short noise, in which case you will write this as sigma t square, and sigma naught square will have only thermal noise because there is no power falling on the receiver. So you will surprisingly realize that the receiver sensitivity actually depends. So you can now think of regular pin diode. Earlier I made a statement saying that it operates in the thermal noise limited condition. You can verify the statement using this problem. You will realize that the answers you get for thermal noise limited operation and the answer you get for short noise plus thermal noise limited operation are almost identical. Whereas, well, you can check it out. You can check it out. What is the difference between the short noise limited condition, thermal noise limited condition, and when you consider for both short noise and thermal noise limited condition. The next question is about avalanche photodiode. So there is an avalanche photodiode. So this is questions 8 to 11. So this assignment is lengthy, but it's mostly formula substitution. So you should make first of all, after going through the videos, you have to make your own notes where you are actually now writing a collection of formulae, and then you should actually use that. The question is the following. You have APD is used as a receiver with a responsivity 1. Photomultiplication gain is given. Excess noise factor is given. Right? So you have all the required information for APD, which is responsivity. Multiplication factor is multiplication factor is 500. And the noise figure of APD, which is a function of multiplication factor, m raised to 0.28. In APD section, we discussed this source of noise, excess noise factor in APD. Detector bandwidth delta F is 10 gigahertz. Load resistance is 100 ohm. Neglected dark current noise and operating temperature is 300 Kelvin. You have to find out the receiver sensitivity. Now, what will be different in an APD? The only difference in APD will be in the short noise. So the way you calculate short noise in the APD is, usually short noise is 2Q, which is the charge of the electron, RD, Pn, which is the short noise current. Now, because you want to calculate the noise in terms of the peak power, what you would do is, because see, in short noise, you want to calculate the noise corresponding to this peak, right? So when you do Pin, you should actually write it as twice receiver sensitivity. Okay, times delta F. This used to be the noise in case of simple pin diode. What happens in case of APD? You will have m square here, and the m square, we also discussed why do you need m square rather than m, because we said it's an avalanche multiplication process, and this m tells you the multiplication in noise because of the avalanche multiplication process, and both the electrons and the holes are participating in this, so there is like m square factor, and then this is something like a noise figure of the APD, and this will give you the sigma short noise square for APD. So you could use substitute this. As far as thermal noise goes, that is the same, which is 4 kT by RL times delta F. There's no change in the thermal noise as far as the APD is concerned. But in short noise, you will have this m square factor. Now, the rest of the question is the repeat of the previous case, where you should now look at, for short noise limited case, you will say sigma naught square is equal to 0. Sigma 1 square is sigma s square. This is short noise limited case. Because there is no short noise, again I repeat, there is no short noise in corresponding to 0, and there is short noise corresponding to 1. And if it is short noise limited, it means that you can neglect thermal noise. The limitation is only because of the short noise. So that is why you had, so the basic principle is this. You have sigma t square here, and you have sigma s square plus sigma t square here. Right? Now, when you talk about the situation where it is limited by short noise, you can ignore the thermal noise. When it is limited by thermal noise, you can ignore the short noise. It's as simple as that. So I think that solves that problem. The next question is 1.3 micron, 1.3 micron receiver is operating at 100 Mbps. It has an effective noise bandwidth of 60 megahertz. Okay, so this is question number is 11. Noise bandwidth is delta F is given to be, this is the receiver electrical bandwidth, 60 megahertz. Okay, this is given. The pin diode has negligible dark current, 90% quantum efficiency, 90%. The load resistance is 100 ohm, and the amplifier noise figure is 3 dB. This is the receiver amplifier. Find the receiver sensitivity, considering thermal noise limited. So you have to do it for 10 power minus 12 and 9, which means Q corresponds to 6 and 7. Now, you don't have responsivity in this case. But I know from my detector theory that responsivity is eta times lambda divided by 1.24. If you can put lambda in 1 micrometer. So I can calculate responsivity from that. Once I know responsivity, I can calculate thermal noise square. It's a thermal noise dominated regime. So short noise is 0. And thermal noise is what? 4 kT by R delta F. But there's one small change here. There is an amplifier which is introducing a noise figure, which means that even in the 0 region, you have, in addition to the thermal noise, you have a multiplication because of the noise figure of the amplifier. And so this is Fn, noise figure of that amplifier. And how much is that noise figure? In linear terms, I do it as 2 because 3 dB is equivalent to 2 in linear units. Right? So you use this. And this is, of course, the load resistance. You know K, you know, it's a Boltzmann constant. Temperature, you know. RL, you know. So delta F is also given. Noise figure is given. You have everything to calculate the thermal noise. Now, if it is in the thermal noise dominated regime, you also know that, what is the question? You want to have a Q. So you want to have a BER of 1E minus 12. And BER of 1E minus 12 actually corresponds to a Q of 7, which means for BER of 1E minus 12, Q is equal to 7. And you know for a thermal noise limited regime, Q square is equal to SNR. This we had derived, or you can just directly write down from first principles. That will also be okay. But then SNR is RD P average square signal power divided by noise power. Right? So you know RD now. You can find out what is the average power. That is what you have to calculate as receiver sensitivity. Sigma thermal square, I just told you how to calculate. So substitute, you will get your Q square as the answer. I mean, you can find out. So you can find out 49 is equal to RD square divided by sigma T square. The only thing you do not know is P average square, and P average is nothing but your P sensitivity, the receiver sensitivity. So this also that way reduces to a algebraic calculation. The last 3 questions are based on EDFA. It operates at 980 nanometer. So this is questions 12 to 14. Assignment is just long, but in terms of the work, it is actually easy work. It operates at 980 nanometer, used to amplify 1550. The small signal gain is found to be 30 dB. You have to be careful when to use dB gain and when to use the linear gain. The input signal P sig in to the EDFA is minus 30 dBm. The EDFA has an optical filter. You can write it as B optical of 50 gigahertz. Remember, we talked about this filter to cut off the AC. The saturation power of the EDFA, PSAT, the largest power that the EDFA can give, is plus 20 dBm. So this information is known. The question is, assuming complete inversion. Now, what is the, assuming complete inversion, find the OSNR at the output, optical signal to noise ratio. So optical signal to noise ratio is, what is the output signal power? That is gain times input signal power, divided by what is the noise power, optical noise power, that is the PAC. Right? So this is output signal power, PC gain. This is output signal power. And this is output noise power. So if I were to use an spectrum analyzer to measure this, this is what I will get. So GP sig in divided by, what is the AAC power? We already said this is power spectral density, rho AAC times B naught. So this is G times P sig in divided by power spectral density is 2 NSP H nu G minus 1 B naught. Now when you do this G minus 1 and G, you should make sure that this is all in linear unit. So convert this into 10 power 3 minus 30 dBm is actually 1 microwatt. So make sure that you are working with linear units. Take the ratio of this, substitute, take the ratio because you have all the quantities that is required. NSP, you can take it as 1 because it is completely inverted. So you can assume that the spontaneous emission factor is 1. So substitute all this. H nu is again, what is nu? Nu is equal to C by lambda. Signal is 1550 nanometers. So you can calculate nu from that. And from that, you can calculate what is the ratio and convert this ratio. So all this you're doing in linear units, convert the ratio to dB scale, that will give you the decibel value. Repeat the question if if the input OSNR is 20 dB and the output input OSNR is 10 dB. So what happens if you have the input OSNR already? It simply means that you're going in with a certain noise power. Right? So if your input has already a certain noise, which means that the noise at the output, so let's say this is P noise, the noise at the output is gain times P noise and plus the noise figure of the amplifier. Okay, so this is P sig, this is G times, this is P sig in, so this is G times P sig in. So what happens is, the noise power also gets amplified, so you have to appropriately consider that. Okay, so the next part is the amplifier is operated under the saturated condition with a gain of 20 dB. Okay, so your amplifier, you're saying that it is operating under the saturated condition. So this is slightly different. So maybe you should pay attention here. What's the meaning of operating under the saturated condition? It simply means that let's say you have a certain length of EDFA, Z is equal to 0, Z is equal to L, right? The way in which the power grows exponentially, you can write it as dP by dZ is equal to some gain times P, right? And let me use the notation G here. Now, I can rewrite. I mean, what is meant by the gain saturation? If you have the gain of the system saturated, it means that as you change your input signal power, the gain does this. That's the meaning of gain saturation. I can see some questions here. I'll get to these questions. Let's get back to this. So we should not get distracted there. So the unsaturated gain, if it is G naught, you can write an expression for saturated as G equal to G naught e power minus G minus 1 divided by G P sat divided by P signal power. Okay, so this is something that can be derived. You can start with G naught and you can find an expression of this is PS which is the input power, right? As the input signal power increases, the gain of the EDFA saturates, and at any power, any input power, the saturated gain gets defined this way. Okay, so you can use this to find out how much gain will you get under the saturated condition. And the other simpler way of looking at it is you get saturated. So the easiest, so this is dBm. So another easiest way of looking at it is, in spite of whatever power you go in, the largest output power you will get is only 20 dBm. So from that also you can calculate what the gains, because you are operating at operating in this saturated gain of 20 dB. So you can very well calculate if my PSAT, which means my largest output power, is 20 dBm, and I'm operating at saturated gain of 20 dB. That's what the question says. This is 20 dB. The unsaturated gain was 30 dB, which means you can now calculate what is the input power. Either use this relation or use a simple information that you have, that your PSAT output saturation power is plus 20 dBm, and you are at a gain of 20 dB, which means Pin must have been should have been 0 dBm, right? So that also you can use to calculate, and then you can actually calculate. So this, even though I wrote this formula, it may not be useful for calculating. It's only for understanding. I wrote what would just be the OSNR. The OSNR would be P out, which is the saturated power, divided by ASC power, right? And when you do this ASC power, so when you do so here your P out, you can't take 30 dB gain. That is the whole point. 30 dB gain will appear only for smaller signal power. In the saturated condition, it is getting only 20 dB gain. So the output power is given. So this corresponds to 20 dBm, which corresponds to 100 milliwatt, divided by ASC power. And you know how to calculate the ASC power. So that's how you go about doing this question. The next question actually gives you a little more details of this saturation. So the same equation, the next question actually gives you in a slightly different way. It tells you that the gain saturation is given by G equal to G naught divided by 1 plus P in by P sat, where G naught is the gain coefficient. So gain coefficient and gain is slightly different. This gain coefficient is simply the e power gz. That coefficient is your gain coefficient. So it's like this. So if I have P out is equal to, I could either write as G P in, or I could write it as P out is equal to e power G times the length of the EDFA fiber times P in. Right, so this is a relation between gain and gain coefficient. You typically represent this in dB or in a ratio. So G naught gives you the small signal, P in represents the input power, P sat represents the saturated power. Given EDFA is known to amplify 1 microwatt to 1 milliwatt. So you already know what is the saturated gain. What is the output power from the EDFA if 1 milliwatt power is fed to it? P sat is given. So for this question, you already have PSAT. So from that, you can calculate what is G naught, right? You know the PSAT, you know what is the input power, you know what is the saturated gain. So from that, you can calculate what is the PSAT. And once, you can calculate what is a P in. And once you know what your P in is, you can calculate what is a P out. Okay. The last one, 17th one is derived in class. So you can just go through the lecture to derive 17th one. 16th one. And 17th one is also something that is derived in class. So you need to go through the lectures. 18th one, SNR is, okay, 18th one is a very interesting question. This is what happens in a link, okay. Find the optical SNR at the end of a 4,000 kilometer link, which has 50 EDFAs. So you have fiber, EDFA, fiber, EDFA, like that. You have 1, 2, etc. 50 EDFAs. Okay. Each EDFA has a noise figure of 4.5 dB. Fiber cable is of loss 0.25 dB per kilometer. Output power of an output power of 1 milliwatt and a 2 nanometer bandwidth. So output power is 1 milliwatt. Okay. Optical bandwidth B optical is 2 nanometer. You have to find out what is the final SNR. What is the SNR at the last stage? Okay. So we derived in class that the OSNR is P signal power minus P noise power, because OSNR is simply the ratio of signal power to noise power. Now we also derived a dB equation for OSNR for a reference bandwidth. So we derived this PAAC out in terms of 158.92 minus noise figure minus gain in dB minus 10 log PO, right? So I'll just substitute that expression which we derived in class towards the end. This is in the logarithmic scale. I'm doing everything in the logarithmic scale because that's more convenient. I'll have to take a minus of all that. So this is 158.92 minus noise figure in dB minus gain in dB minus 10 log 10 B naught. This 158.92 came from converting that h nu times logarithm of that h nu factor in the PAAC term. There's nothing drastically different here. All what you did was you converted this PAAC 2 NSP into G minus 1 into B naught. What you did was 2 NSP you calculated. This is the noise figure. H nu is what that 158 gave you. G is still there, approximated G minus 1 as G, and this B naught is still there. So all what you did was to write this in the logarithmic scale so that it becomes easier for calculation. Now you want to find out what is the OSNR at the output. You do have all the information. You know what is the output power. It is 1 milliwatt, so that is 0 dBm. Noise figure is given for each EDFA. Gain is not given, but you know that the fiber loss is 0.25 dB per kilometer, which means that 50 kilometer times 0.25 dB per kilometer is should have been the gain of the amplifier. So you can calculate what is the gain, and of course B naught is given. Right. So this is actually useful for link design, and that completes the assignment discussion. Now, what are the other questions that I have? I have which dispersion compensation technique is better? Pre-post symmetry, DCF or FBG? So that probably comes later in the course. So if you do not consider nonlinear effects in the fiber, there's no difference between the different dispersion compensating technique. But if you have nonlinear effects in the fiber, then you will realize that probably distributed compensation is better. Please make it available for download. So that I'll request the NPTEL team, please make the videos available for download. I think that is, if it's not available, I'll let them know. Can the ring magnitude of laser at modulation bandwidth be added to short noise? No, we consider the source of short noise is completely different. It's quantum mechanical. It's because of the arrival time of the photon. If you wanted to add the ring noise, it should be added separately. It should be added as a separate source of noise. Photon lifetime depends on cavity length mirror reflection. If I make a cavity greater than the metastable lifetime, there won't be any stimulated emission. Yes, there won't be any stimulated emission. There won't be any lasing if you keep the cavity very, very poor. Yes, that is correct. I mean, the threshold will be so high that you may not really reach the threshold. Okay, are there any other questions? If there are no more questions, I will log off now. All right, see you next week.